This week we'll be covering material that's from more than one chapter in the book. When we look at the contents in the book, chapter 2 covers atoms, and then the beginning part of chapter 3 contains information about ions, and all that an ion is an atom that has either gained or lost electrons and therefore has a charge. And when an atom becomes charged, then it has its own unique properties. Well, there's something in chapter 2 that we've skipped over, and that is radioactivity. Okay, now it does fall back on a knowledge of mass number and atomic number. Atomic number is the number of protons in an atom. Protons, you'll remember, are the positively charged particles in the nucleus. And the mass number, the larger of the two numbers for any particular atom, is the combination, the sum of the protons and neutrons. Okay, well, there are three major types of radioactive decay. This is the type of radiation that's called fission. Fission happens, we mentioned very early on in the previous video, that when the number of protons in an atom gets to be significant, then the repulsion inside the nucleus can actually rip the atom apart. And we're going to turn heavy atoms into atoms that are lighter. This process turns an isotope, or a nuclide as they're called in the nuclear industry, that it is a mother, into something that is known as a daughter. Okay, the first one that we'll look at is alpha decay. Now, an alpha particle is the largest type of radioactive particle, and it looks suspiciously like a helium, except it doesn't have any electrons. So the alpha particle itself has a mass number of 4 and an atomic number of 2, and it looks kind of like a helium, but it can't be a helium atom. It has no electrons. This is something that is expelled from the nucleus, and we know that electrons don't live at the nucleus. Okay, so this is going to turn out to be quite simple, because the daughter that lives in this blank space right here is subject to something that we call mass balance. That the amount of matter on the reactant side has to equal the amount of matter that is on the product side. So some number up here for the mass number goes here. That is a number that when you add 4 to it is equal to 242. Some number that when you add 4 to it is equal to 242. So that number gets to be 238. And then the number at the bottom, which matches the atomic number that goes here for whatever our unknown daughter is, when you add 2 to it, equals 94. So a number that when you add 2 to it equals 94 gets to be 92. Okay, so we have two numbers now, a mass number and an atomic number. And when we go hunting on the periodic table for whatever this daughter nuclide might be, we remember that the mass number is variable. It's only the atomic number that is fixed and is an integer. So it's the atomic number that we're going to use to identify our atom. And if we look down here, way down at the bottom, we find that atom number 92 is uranium. Now, radioactivity is a naturally occurring process, and atoms from all over the periodic table can be radioactive. But if you're way down at the bottom and you're very, very heavy, you're pretty much guaranteed to be radioactive. So lots of our examples are going to come from the bottom part of the periodic table. Okay, and at this point, let me make that 2 look more like a 2. At this point, we think that we have completed this equation. That plutonium-242, which has an atomic number of 94, loses an alpha particle that has a mass of 4 and atomic number of 2, kind of looks like a helium, and leaves a daughter of uranium-238-92. But there's something missing. Something that even our book doesn't mention. That every time an alpha particle is given away, it also emits gamma radiation. Now, alpha, and for that matter beta that we're going to see in a minute, they are particles. They have mass. They have quantifiable mass. But gamma rays are just pure high energy waves. And we can't really predict how much gamma is going to be given out. And each of these 3 types of radiation, the alpha, the beta, and the gamma, are all dangerous to us in different ways. The alpha particles, because they are the biggest, the slowest moving, they're not very much of an exposure hazard. So if this were an alpha emitter, I would just move myself away from it. And if I had to be in the presence of it, I would just put something in the way. And you can block alpha particles by a piece of cardboard. Okay. Now, if this is just a solid, then I'm okay. But if it were to be dust or any kind of particulate matter that then entered my body through my nose or through my mouth or through an open cut, that would be incredibly dangerous, because as an ingestion hazard, alpha particles are incredibly toxic. So alpha particle is an ingestion risk, but is not an exposure risk. Can't ingest a gamma particle because a gamma ray because they're not a particle. They don't have matter. These are a very, very extremely dangerous exposure hazard. Gamma rays are higher in energy than X-rays. Betas, we're going to find out in a minute, somewhere in the middle, that they are more of an exposure hazard than alpha, less of an ingestion hazard than alpha. Okay, let's do another one of these. Let's go back to an alpha. We've just found out that plutonium can undergo alpha decay and make a uranium. So I put the uranium right here. That daughter that we made in the first step is now the mother of a subsequent step. Let's just go figure out what those numbers are. Okay, so I know that there's going to be an associated gamma emitted with this alpha decay, and that the alpha has numbers 4 and 2. So 238 is equal to a number that goes here, that when you add 4 to it is equal to 238. So this gets to be 234. Okay. And then some number, when you add 2 to it, is equal to 92. So the daughter of the alpha decay of uranium-238 has numbers 234 and 90. And we go and we look on the periodic table and we go and try and find atom number 90. because we don't search on the periodic table by mass, we search on the periodic table by atomic number. And position number 90 is thorium. TH. Okay, that's how we do an alpha decay. Let's look at a beta decay now. Beta decays do something similar, only the numbers here are different. Beta particles are much, much smaller and much lighter than alphas. And they have numbers 0 and -1, because a beta particle looks suspiciously like an electron. Now we know it cannot be an electron because the beta particles come from the nucleus. When the nucleus splits apart, it emits this particle, and we can't have electrons be at the nucleus. But it looks really like one. And when we look really carefully, we can see that neutrons and protons don't weigh exactly the same amount, that they differ from one another by the mass of an electron. So when a neutron turns into a proton, it emits an electron. This is going to push our numbers in a different direction than alphas did. When we look on the periodic table, we started at plutonium, and we moved down to uranium, and then we moved down to thorium. We moved from a heavy isotope down to a lighter isotope. Beta decay is going to push those numbers back in the opposite direction, which is probably a key why we need both of them. There is a particular element of interest on the periodic table. Lead. Lead is right there. Lead is the last stable isotope on the periodic table. Anything heavier than lead is spontaneously radioactive. So all of these atoms up here that are heavier than lead are going to move zigzag, and they're going to find the way back down to lead. All right, let's put some numbers in. So there's going to be a mass number and an atomic number for the daughter nuclide of this decay. And the number that goes up here up top, when you add 0 to it, equals 238. So 238 plus 0 is 238. And some number here, when you subtract 1 from it, equals 92. So those are our two numbers, the mass number and the atomic number, for our nuclide. And we started at uranium. Uranium is here. And we took a step back to neptunium. Okay, let's do another one. This is americium 243.95. It's, oh, yeah, don't forget there's a gamma. It's going to emit a beta particle, and the beta particle has numbers 0 and -1. So our mass number of our daughter nuclide stays at 243, and the atomic number of my daughter nuclide goes up. And I look, and I find, where are we? That americium has turned into curium. Americium at 95 has turned into curium at 96. Not CU, CM. I almost made that be copper. That would be completely wrong. Along with every alpha and every beta emitted from the nucleus, you also get gamma radiation. Okay, so as a recap, these are our 3 types of radiation. They're called alpha particles, beta particles, and gamma rays. Gamma is a very high energy wave that is emitted during both of the other 2 processes, the alpha fission and the beta fission, radioactive decay. The daughter nuclides of every reactant, mother reactant, can be found just by knowing what the numbers of the mass number and the atomic number of the particles are. Alphas are very similar to helium nuclei, and betas are very similar to electrons. Alphas are not an exposure hazard, but are an ingestion hazard. Betas are a mild exposure hazard and a mild ingestion hazard. Milder. Okay, if you have questions, let me know.